Hello, hello everyone. Myself Reshu, and the topic for my presentation line of curvature and Rodrigue form, and my roll number is 195047. So first of all, differential. A curve on surface is called a line of curvature if the tangent at any point of it along the principal or direction at that point. Since there are two principal directions at each point other than the umbilic on the surface, they are mutually perpendicular. So we have a two system of line of curvature on the surface. Now equation of line of curvature. Since there are two principal of direction at each point of line of curvature, at any point is along the principal direction at that point, hence the differential equation of the point system of the two system of line of curvature is the same as the equation of the principal direction. So the equation is bracket em minus fl bracket close du square plus bracket en minus gl bracket close du dv plus bracket fn minus gm bracket dv square is equals to 0. This equation can be written in the following form. That is, we can take out its determinant, that is the determinant dv square minus du square e f g l m n is equals to 0. Again, bracket fn minus gm bracket close minus f bracket en minus gl bracket close plus g bracket em minus fl bracket close equals to 0. Therefore, the two system of lines of curvature are orthogonal. Now theorem or Rodrigue formula. A necessary and sufficient condition that a curve on a surface B line of curvature is that dn cap plus kappa dr is equals to 0. Its proof is let du comma dv be a line of curvature on the surface, then it is a principal direction at point u comma v to that surface. Hence we have form equation that is bracket l minus kappa e bracket close du plus bracket m minus kappa f the bracket close dv is equals to 0, and bracket m minus kappa e du plus n minus kappa g bracket close dv is equal to 0. Substituting the value of e f g l m n in terms of derivatives of r and n, that is e is equals to r1 square, f is equals to r1 dot r2, g is equals to r2 square, l is equals to minus n1 r1 plus m comma m is equals to minus n minus n1 r1 square r1 मतलब r2 is equals to minus r n2 dot r1 comma n is equals to minus n2 dot r2. In the previous equation we get bracket minus n1 dot r1 minus kappa r1 square plus du into du plus bracket minus n2 r1 minus kappa r1 r2 bracket close dv is equals to 0, which can be written as that is bracket n1 bracket n1 du plus n2 dv dot bracket close r1 plus k plus kappa bracket r1 du plus r2 dv bracket close r1 is equals to 0. Now we can also write it as bracket dn dot r1 plus kappa dr dot r1 is equals to 0, which is further equals to dn plus kappa dr dot r1 is equals to 0. So by solving this we get dn plus kappa dr dot r2 is equals to 0. Since n dot n is equals to 1, therefore differentiating we get 2 n dot dn is equals to 0, that is dn is orthogonal to n, or dn is tangent vector. Also dr is a tangential vector, so the vector dn plus kappa dr is equals to 0 is a tangential to the surface. Therefore, in order to the equation 3 and 4, that is 3 and 4 are satisfied, we must have dn plus kappa dr is equals to 0, which is a necessary condition for the curve to be line of curvature. In order to prove that the condition is sufficient, also consider a curve on the surface at every point of which we have dn plus kappa dr is equals to 0, where kappa is any function. Taking reverse orders of steps, we get equations 3 and 4, which are expressible as bracket L minus Ke bracket close du plus bracket M minus kappa E bracket close dv is equals to 0, and bracket M minus kappa F bracket close du plus bracket N minus kappa g bracket close dv is equals to 0. Thus the curve is the line of curvature in case kappa is normal curvature to the surface. It is given that the dn plus kappa dr is equals to 0, which gives kappa dr plus dn is equals to 0, which is further equals to k dr is equals to minus dn. Kappa bracket r1 du plus r2 dv bracket close, which is equals to minus bracket n1 du plus n2 dv bracket close, which further we can write it as kappa bracket r1 du plus and plus n2 n2 dv bracket close into bracket r1 du plus r2 dv bracket close, which is equals to minus bracket n1 du plus n2 dv bracket close into bracket r1 du plus r2 dv, which can further written as kappa bracket e du square plus 2 f du dv plus g dv square, which bracket close is equals to l du square plus 2 m du dv plus n dv. Now kappa will become equals to l du square plus 2 l du square plus 2 l du square plus 2 m du dv plus n dv square bracket e du dv square plus 2f du dv plus dv square. Therefore, the kappa is normal curvature at the point u comma v in the direction du comma dv. This shows that the direction of the curve at any point is a principal direction. Hence, the curve is a line of curvature and the given condition is sufficient. So this kappa is we have calculated this kappa, and therefore our theorem is proved. So thank you everyone, and thank you so much.